neural network topologies. So different algorithms that solve the same problem, right? And they're implemented with different precisions. Okay, and what you find is if you apply the applications constraint to these networks, let's say, for example, I can't tolerate more than 10% error. What is the best thing you can do for me? And then I look at my networks. I might have a ResNet, okay, let's say it's 11%. So ResNet 18, 8-bit, 8-bit has a compute cost of 286. Now ResNet 50, so a larger network, but to reduce precision of 2-bit and 8-bit, has a less than half the compute cost, and it's better in terms of accuracy. So there's compromises that you can exploit when you actually look at the full design space. Okay, so now very briefly in the last few minutes, let's take a look. And I'm literally just going to do an overview of what happens on the hardware architecture side to help support the application. There is going to be much more detail now in part 2 and 3 about the hardware architectures. So first of all, there's a whole spectrum of architectures. So there's the good old ones like the CPUs and the GPUs, right, which are vector-based SIMD processors, but I think you all know this. Then we have specialized compute architecture. So Microsoft coined the term deep learning processing unit, or DPU for this. I quite like this, so I'm going to stick with this one now for a bit. And then you have the really esoteric ones, which are the in-memory compute, which build on memristors or stacked DRAM technologies. And I have all the references here, so feel free to go and dig them up, but I'm not going to cover them here. So coming back to what you see here, the deep learning processing units, they can be both soft, so programmable architectures with FPGAs, or they can be hard, so ASICs. And there's many of those you might have heard about, like Google's TPU. There's Cerebras, GraphCore, Grok, Nirvana, with computing, Mobilius, Kali, yeah, you name them. And I'm throwing them all in the bucket, which is strictly speaking, they're quite fundamentally different. But let's say they're all customized for the specific task. The other thing I want to point out, this is turning into a huge blend of architectures, because even when you look at your GPUs, they're increasingly being customized for deep learning. So you heard probably the Turing announcement, which now supports enforced reduced precision. You have tensor cores in there, and so on. So this is all going to blend eventually. So there's a number of choices you have to do. Let's say you were to design the next AI accelerator. A couple of ones I wanted to point out is one, on the macro architecture level, you can choose between a data flow implementation and a matrix of processing engines. They're kind of at the extreme end of the spectrum. There's a lot of combinations in between, but just to look at the endpoints to get the point across, the matrix of processing engines, right, brings a certain amount of flexibility as you can schedule any neural network on top of that. Whereas the synchronous data flow is literally customized towards a specific topology. You literally instantiate every layer in your device over a sequence of devices. Very prominent is Microsoft Research. Brainwave that falls into this. In my research team as well, we're working on FIN. Maybe you've come across it. So they would be in the synchronous data flow end of the spectrum. And the beauty of this is that you can really reduce the amount of activation buffering that we have, because you just need to have enough data here so that the next layer behind you can start the convolutions, okay? So that brings reduced memory cost. It also reduces the latency that you're gonna have as the data propagates through the neural network. It's also more compute and memory efficient because you literally customize for one specific topology, whereas if you have a generalized architecture, you can't cater for the specializations in the different neural networks. Like even between layers, if you look at ResNet 50, one layer has 60 channels, the other one has 2048. What you're gonna do, right? You're gonna cater for the worst case. And those are the questions you have to answer. The second choice you can do is on the microarchitecture level. So you can literally customize the arithmetic with which you compute. And I put an arrow actually on the GPU because they're doing that now as well. So customizing the arithmetic for neural network accelerator is already happening, so you might have heard about Nirvana's FlexPoint, Microsoft custom floating point format, bfloat16, there's all sorts of things happening. So if you were to build your accelerator, which one would you support? I mean, these are really hard decisions, right? Because you can't support many of them because it's too costly again, you lose your efficiency. And if you fix for one specific one, it's pretty risky, right? I mean, there's a choice to be made. What's more so, it turns out actually that non-uniform quantization across the layers of one single neural network is actually beneficial in terms of accuracy. So you can take, for example, 4 more bits in the middle of the network than at either end of the spectrum. Okay, so the trick that you could do is what's called bit serial. Now this is also not new, this is from signal processing, probably something like 20 years ago. And the idea is simple. So rather than actually feeding the operands parallel into your multiply accumulate, what you do is, which you have there on the left-hand side, you feed them lengthwise, bit by bit into your multiply accumulate. And what happens is that the multiply accumulate gets minimal, right? It becomes really small, and then it can instantiate many more of them. So there is a trade-off between latency and resources. And what we found when implementing this in FPGAs, there's almost no cost and overhead to doing actually the runtime programmable bit precision. And the chip level, bit level performance that we're going to get for low precision is basically equivalent, yet we have the runtime programmable bit precision. Okay, this is just to throw out some of the ideas of what you can do at the architecture level. So let me sum up before I hand you over to my colleagues. So CNNs are increasingly being adopted all across the board on new workloads, and you say that, and the key to the industrial revolution right now and perhaps even the next one. However, they are associated with significant challenges, and I won't iterate them anymore because no doubt it was a long list. It requires creative thinking on all of our behalves, algorithmic architectural innovation, co-design, and because of this, we're now facing an emerging spectrum of specialized compute architectures and algorithms that try to address this. One thing I would like to leave you with today is the need for defining clear metrics that allow us to actually do adequate comparisons between these endpoints in the solution space. So the hardware performance always needs to be tied back to the application level performance because you need to provide the algorithmic freedom to optimize for all this broad range of different types of hardware architectures. And ideally, you don't just compare one endpoint, but you actually visualize and fill out that design space so that depending on your specific application requirements, we can actually pick the optimal solutions along the Pareto curves. So it's exciting times for our community, many new architectures evolving, programmable or not. So finding the optimal solution here within this multi-dimensional design space is the name of the game. And with that, thank you very much for paying attention. My colleagues continue.
Yeah, looks like we have one over here. And if you could identify yourself, please, and your affiliation.
Well, Michael Shea from UC Berkeley Extension. Thank you for the excellent talk. I learned a lot out of it. Question here is, watching all these things, you have provided the formula. Essentially, there are matrix multiplication. So, how do you prove all these things, all these algorithms would always converge? I mean, meaning that eventually they will all...
No, there's no guarantee on convergence, right? And many times when we start training neural networks from scratch, you might not get convergence because you have to initialize it in the right way, you have to have the right choice of hyperparameter settings and so on. So it's actually really important when exchanging neural networks that you provide the full training script which have the full hyperparameter settings.
So it's purely trial and error? Trial and error approach. I mean, try it and.
Yes, so there is a certain amount of, it's fair to say, right? There is a certain amount of...
We call it an empirical science.
Nice.
Well, I mean, given that, then how do I, as a system designer, how do I really try to put all these processing units all the way to the edge? Because I mean, for IoT world, I mean, what you really want to migrate all these calculations all the way to the edge. I mean,
You mean like distribute the workload between the cloud and the edge?
yeah.
Is that what you mean?
Yeah, push it all the way to the edge. Compute.
So that's our next segment.
Yeah,
That's a great segment.
yeah, that's a great question.
Another question over here?
Yeah, my name's Oliver Gonseca from NGCode. Thank you for a great presentation. A quick question, are you optimistic that MLPref will provide the benchmark to help us compare different architectures?
MLPerf, oh yeah, it's definitely going in the right direction. I've been following it actually very closely. This is a subject I care deeply about. So I see, for example, concepts emerging, the open versus closed model, which I think is in that step of actually providing the freedom for algorithmic optimization, which is going to be, anyone who works on heterogeneous hardware architecture knows that you can't just take naively an algorithm and run it on a platform. You actually